today lecture 8, and today we'll continue. I'll just say it is 8 and 9. Okay, so in this is the Rayleigh method, which is count for the masses that were previously ignored. So it is called, when you get the mass, you call it effective mass. There are two types of systems here that we can get the effective mass. The first one is called discrete, when the masses are point masses or lambda masses, or they are rigid bodies. And there is a distributed mass parameter system, like when you have a flexible beam or springs. So we'll talk about the idea first, using an example of a discrete, and then we will move on to the distributed mass parameter system. The discrete, here some examples is that when you add masses, this is very trivial. And when you have a rigid body, like a link here, or this is a bar, rigid bar, and it carries mass 1 or 2 or more, then the masses on the rigid bar their motion are related. They are not independent. Although we have more masses, but this become a single degree of freedom system because the motions of all the masses are related. Okay, here is an example of just one link and the mass. Okay, so you can have, for example, here we have a rigid link or bar pivoted at point O. So let's say this is MA and MB, and of course this should be supported here by springs, something like that. Then the motion of MA, MB, as well as the bar, if it is not massless, it is rigid, but it can be massless or it can be not massless. So the masses A, B, and the bar are their motions are related from the dependent motion because you can construct the similar triangles, and then XB is related to theta. Right? You can write here XB. Okay, let me start with, if I give this distance is LA, and this is LB, then XA equal to, you can construct a right angle triangle right here and here. Then XA equal to LA sine theta, and XB equal to LA sine theta, LB sine theta. So as you can see, XA is dependent on theta, and XB is also dependent on theta. The bar is rigid, so all the points on the bar are rotating with angle theta because it is rigid. Then we have single degree of freedom system here, although we have many masses. We usually, for small oscillation, we approximate sine theta as theta to make it linear. Okay, so this is LB theta. Okay, the equivalent system to this can be either a spring mass system Okay, so in terms of XA, for example. So you can get equivalent system as a translational system, spring mass system. Okay, equivalent spring mass system at A. Then it will be a spring with spring K effective and M effective. Okay, M effective, and it is moving with XA. Okay, or you can find the K, an equivalent spring mass system at B or at any other point. So with this, this is an equivalent system, or you can get an equivalent system torsional, rotational, like a disc and a shaft. Okay, equivalent torsional system. Which means you will have a disc and a torsional spring, KT. So this will be J effective, and this will be KT effective, and this will have that, and the disc is rotating with theta. So the idea is to reduce if you have a rigid body carrying masses, or you have, like, for example, gears here, gears in mesh, then their motions are related if A, gear A is rotating with theta A, then gear B is rotating with theta B, but those are two coordinates are related. Okay, so suppose there is a spring here, KT, then this becomes oscillatory system. Okay, so you can get J effective for this system in terms of theta A, or you get another system, another disk equivalent with J effective. Okay, I can say JA at JA, and this is JB. I just gave them different name, but these are effective, يعني, effective at A, and this is JB effective at B, and the torsional spring. But this is KT at B effective, and this is KT at A. So either any one of them is, we are reducing, instead of having two variables, two coordinates, we have only one coordinate, and this is possible because those are rigid and their motions are dependent. Okay, so how to get the equivalent system is by using the kinetic energy. Okay, so we have here, if I go back to this system, XA and XB are related from the similar triangle, so you can write that XA over LA equal to XB over LB. Okay, and that XA equal to LA theta and XB equal to LB theta. Those are the dependent equations. So if you want to get a system in terms of equivalent system in terms of XA, then you will use this equation to find XB in terms of XA, which is LB over LA times XA. And also you will get that theta equal to equal to XA over LA. Okay, so those are the relationships from which he can write the kinetic energy. Okay, so the kinetic energy of the system will be wherever there is mass or there is mass moment of inertia, the kinetic energy has to be counted. So we have MA, then it has a kinetic energy, and we have MB, so it has also kinetic energy. If the bar is not massless, then it has a moment of inertia, has a kinetic energy in rotation. Okay, so the equivalent system is first of all has to we have to determine the point at which we want the equivalent system, and then we find the kinetic energy. So the kinetic energy for A is TA has a kinetic energy 1/2. This is a point mass, so it is 1/2 MA XA dot squared, right? And the mass B has a kinetic energy. Okay, I just call it TB equal to 1/2 MB X B dot squared, and the moment of inertia for the bar is T for the bar equal to half JO theta dot squared. The total kinetic energy, as you know, for any system has to be added. The all kinetic energy, we have to add them. So the total kinetic energy will be, TA plus TB plus TB for the bar. Okay, if the springs are massless, then there is no kinetic energy. Okay, if their masses are not neglected, then their kinetic energy has to be. If their masses are not neglected, then their kinetic energy has to be counted. And you can substitute with TA, TB, and TB, and then replace XA dot, because you can differentiate. And this is the displacement relationship, which also means that X dot B equal to LB over LA X dot A. And the same thing here, theta dot equal to XA dot over LA. And then you will collect the similar terms. Okay, and you will end up with 1/2 and some terms here added together, multiply by XA dot squared, because this will be the common factor after we substitute of X dot B in terms of X dot A, and after we substitute of theta dot in terms of XA dot, we can take XA dot as common factor. And make sure that you keep the factor half in front, and then X dot A square at the end, it's also a common factor. And then whatever inside is called M effective, which is getting the spring mass system. Okay, so this has a kinetic energy T equal to 1/2 M effective XA dot square. And if suppose you want to get the torsional system, then this will have a kinetic energy 1/2 J effective theta dot square, which means replacing the kinetic energy is the same, which is this one. But if you want to get torsional system, you will replace XA in terms of theta. And if there is, that is XA dot in terms of theta dot, and XB dot in terms of theta dot. And then theta dot becomes a common factor, and you have to keep the factor half in front of J, then that will be the kinetic energy. And and in between the factor half and theta dot square is the J effective. All right. So those are for discrete masses. The idea is that here as mentioned, in system in which masses are discrete, which are joined by rigid links or levers or gears, those are all rigid components. The motion of the various masses you will have M1, M2, whatever, MA, MB, can be expressed in terms of the motion X of some specific point. You can, if the question is to find the equivalent system at a specific point, that is the one you have to use, okay, in terms of that point. And the system is simply one of a single degree of freedom system, because only one coordinate is necessary. All the other coordinates or all coordinates are dependent. So you just select one of the coordinate to be the main coordinate. The rest will be replaced by in terms of that coordinate. And then the kinetic energy can be written as T equal to half M effective X dot square. So you keep this factor in front, and you take the coordinate or velocity of the required point at the other as a common factor. Okay, where M effective, this is M effective here is going down, is the effective mass or an equivalent lambda mass at the specified point. Okay, so once you reach the spring mass system, okay, if the stiffness at that point is also known, the net shear frequency can be calculated from the simple equation omega n equal to square root of k over m effective. Now, if it is known, you know, if the stiffness is known, if the stiffness is also not known, it means you can use potential energy, okay, to find k effective, use potential energy. Okay, the potential energy is that U equal to 1 over 2, it becomes K effective times X squared. So it's the same idea. To get the mass effective, we obtain the kinetic energy and replace coordinates in terms of one specific coordinate. The same thing for the potential energy. You obtain all the potential energies of the system and then add them together and replace the coordinate in terms of that specific point. Okay, the example is, okay, the example is we have a rigid massless link pivoted here, and there is a torsional spring. Okay, and it carries different masses, 3 masses. Okay, so this is M1, M2, M3, which are located at distances L1 and L2 and L3. The bar is rigid. Okay, assume it is massless. Okay, assume massless. Okay, so I don't know if this is the net shear frequency. Once you reach spring mass system, omega n is equal to square root of k over m effective. If in case that k effective has to be obtained, then omega n will be square root of k effective divided by m effective, if it is required to obtain the effective stiffness at that point. Okay, as in this example. Okay, so there is rotation, the bar is in rotation, but since it is rigid, it's going to carry the masses into equal or proportional displacement. So if suppose we take the equilibrium, this is the equilibrium, this is the horizontal equilibrium line, and this is KT, and this is torsional spring. So at an arbitrary position, okay, which is, this is at angle theta, the distance moved here is x3, and the distance moved here is x2, and the distance moved here is x3, is x1. And for small theta, you can, take the relationship that similar triangles. Okay, this I will use different color. This is the similar. This is triangle number 1, and this is triangle number 2, and this is a triangle number 3, or are all are similar triangles. So you can get x1 over L1 equal to x2 over L2 equal to x3 over L3, as well as, since I'm using massless bar, then that kinetic energy is not counted. But also we know that theta, now suppose I want to find equivalent system bearing mass system at M1, which means in terms of X1. Of course, this relationship can be differentiated to get the velocity relationship. That is X1 dot over L1 equal to X2 dot over L2 equal to X3 dot over L3. The kinetic energy will be T equal to 1 over 2 M1 X1 dot square plus 1 over 2 M2 X2 dot square plus 1 over 2 M3 X3 dot squared. And as you can see, I can take 1 over 2 common, and this is M1, and I would take X1 dot squared common, that will be plus M2 times X2 dot squared, right? X2 dot can be obtained from this relationship. So what is X2 dot? X2 dot is equal to L2 over L1 X1 dot. So this will be times L2 over L1 squared times X1 dot squared, which I will take it as a common factor. Okay, so plus M3 times X dot 3 is related with X1 dot, so it is X dot 3 X3 dot equal to L3 over L1 X1 dot. Okay, so we will use this relationship to replace X3 dot. So it is L3 over L1 squared and X dot 1 squared. So X1 dot is common, so this will be outside the bracket. So as you can see, there is M effective here between the factor half and X1 dot squared, and that is the M effective. And in terms of this equal to 1 over 2 M effective X1 dot squared, and whatever we have in the bracket, in the curly brackets, is the M effective. So that is the M effective here. it is M1 plus M2 times L2 over L1 squared plus M3 times L3 over L1 squared. To get the spring equivalent at M1, we need to use the potential energy. Potential energy is what? We have, of course, do not put mg because the M1g and M2g are balanced by the torsional spring in equilibrium. So here we are, whenever you have a rigid bar supported horizontally, then carries masses, then the equilibrium line is either horizontal or inclined, but it means that the weights are countered, balanced by the springs we have, the forces in the spring or the moments in the spring. This is a torsional system. The gravity forces, the weight will have moments about point, let's say this is point O, and it will be counterbalanced by the torque provided by the shaft. So if you want to include the weights, it means you have to include also the spring, which is at equilibrium. So we know that for horizontally supported masses or object, that the weight is not part of the equation. So the kinetic energy is only due to the strain energy of the spring, which is torsional spring, which is half kT theta squared. This is torsional, and kT, unit of kT is a Newton meter per radian. Okay, and here we need to replace theta in terms of x. We cannot have two different coordinates, just one coordinate. Theta is equal to L1 equal to x1 over L1. Okay, for small theta, and this is true for theta very much smaller than that. Okay, so this will be 1 over 2. This is to make the system linear. 1 over 2 kT times theta, which is x1 squared divided by L1 squared. So as you can see, the K effective, we keep the factor half, and between parentheses, we have kT over L1 squared times x1 squared, and that will be K effective. Okay, 1 over 2 K effective times x1 squared, where K effective is kT over L1 squared. Now you can check the units. This will be Newton per meter, because kT is in Newton meter per radian, and radian is not a unit. Okay, so units of it's Newton meter per radian. Okay, I'm just reminding you of the units. And when you see the K effective should be a spring mass system, and the spring should be in linear motion, which should be Newton per meter. So it is Newton meter per meter squared is going to be Newton per meter. And once you reach to this system, you know that omega n equal to square root of K effective divided by M effective. Okay, that's it. If you find torsional stiffness, torsional system with about O, it means there is no need for getting K effective, because that K is KT directly, but you need the kinetic energy. The kinetic energy expression or the potential energy expression will be different if you choose another point, let's say you choose point 2 or M2, then the shape of the expression will look different. But the final equations will be the same. You know, omega n at the end, it will be square root of K effective over M effective. And if you have numbers, you will get the same result. Even the kinetic energy, potential energy are the same. Whether you use x1 in terms of x1 or in terms of x2 or x3 or theta. Okay, so this is an example of reducing this system into spring mass system. Any questions?
دكتور
Yeah, go ahead.
في المسألة اللي قبل هاي المسألة خليت ان تان ثيتا تساوي ساين ثيتا.
ايه
هل دكتور هاي الشيء دائما يعني الحين المسألة ليش ما كتبنا السيدة يعني ان تان ثيتا وبعدين قلنا for small oscillations اقول تان ثيتا تساوي ثيتا؟ ليش حولناها لساين ثيتا قصدي؟
في المثال اللي قبل اثنين.
اي دكتور.
اوكي، هذا ال A equal to sin theta مثل ما قلت لكم قبل، يعني any for theta very small. يمكن هنا أنا ما ذكرت، بس يمكن maybe I said it يعني theta very much smaller than 1, then sin theta equal to tan theta equal to theta. Okay, the same thing. This is the linearization method that we are following. Yeah? So this will be sin theta equal to tan theta equal to theta. This is approximately for theta very much smaller than 1. Okay, it's the same thing here and in this example as well. كان هاي سؤالك حسن؟
اي تمام شكرا.
We have tutorial number 4, which is about equivalent or effective mass. Some of the questions are related to discrete, okay, and some are related to distributed mass parameter. Now, what do we mean by distributed mass parameter? That they are flexible as one point, and that their mass is distributed along the length of the member. So we have springs; those are elastic members. Beams are also elastic to some extent. We assume they are rigid. If they are like pivoted, their motion is neglected. يعني their relative motion points. This is pivoted, right? This bar, we assume it is rigid because it is pivoted. And that the relative motion of the points on the bar are very small compared with the angle theta. And this is why you can assume rigid. Okay, and also it should have a high moment of inertia, I, the cross-sectional area of the cross-sectional area. But for members not pivoted, like the beams, we have cantilever beam. Okay, we know this will be not rigid because the relative this is zero, this deflection here. This is fixed. Then that y at 0 is 0. There is no pivot here. So the points will have relative motion. Okay, it means this is elastic. And of course the spring is elastic. Okay, simply supported beams also will have zero displacement here, zero displacement here. But if this is loaded, as was the cantilever beam, then there will be relative motion deflection. This which will make a deflection. Also, the cantilever beam under this load will make a deflection. Okay, and simply supported is this one, cantilever, fixed beam, or any other configuration. and boundary conditions. The spring as well, if this is fixed here and support a mass at the top, then the points on this the spring are relatively, they are moving because this is fixed. Okay. Now the question is, if those are the masses are not neglected, and of course they are not rigid, and this is what we did in the beginning of the chapter, that we obtained equivalent stiffness, but this bar has no stiffness, and the reason is that it is pivoted. The relative motion is zero, or assumed to be zero, between the points on the bar. But since those members are supported, they have boundary conditions, and they are not pivoted. Okay, the pivot will make them under rotation. But if they are supported at boundary conditions, at the boundaries, so they will have deflection. They will deflect. And then if their masses are neglected, then and this was the assumption before, that their masses are neglected, then we only assume them as the springs. So they have K effective or K equivalent equal to 3EI over L cube. And I showed you this, and this has a stiffness at, if you place the mass here at the middle, this will give you a stiffness K equal to 48 EI over L cube. Okay, and the spring also has a stiffness either by the design equation or by Hooke's law. But if their masses are not neglected, the spring mass is not neglected, so it has ms. The beam mass is not neglected, then it has mass mb. Okay, the same thing for this example, the simply supported beam. But the mass is not located at one point. It is distributed along the length of the beam, or along the length of the spring. Now, if we assume, okay, before the assumption that since we have the masses are not neglected, then the kinetic energy is not zero. So beside those elements are acting as or representing a spring, like the beam and the beams, they are acting as springs. Their masses cannot be ignored if their mass is not zero. So their kinetic energy cannot be ignored. The same thing for the spring. Okay, the spring has a stiffness K. Yes, I have شير عندي هنا. Okay, just give me a minute, I will come back. Okay, this my laptop is stuck, so I will come back. This one note is every time between while and between time and a while, this will give me this. Okay, so I'm back. Sorry for this. Okay, so we have the examples about a cantilever beam already we did in the beginning somewhere, maybe here. Yeah, this was one of the examples. And okay, this was another example that we have a cantilever beam with the mass at the end, and the mass was neglected, but it is flexible, so it is providing a stiffness. And then the initial frequency is equal to square root of k over m, and k is obtained by the k equivalent, which is 3I over LQ. Okay, so the additional thing here is that their masses are not neglected compared with the mass we have. Rayleigh method is before that those elastic members. Maybe obviously we can talk about a simply supported beam. A simply supported beam, it can vibrate. We know that those points are always zero. So it can vibrate as a half sine wave. Okay, this is. So it can vibrate as a, this is the equilibrium line. So it can vibrate as a sine wave, as a half sine wave, below and above the equilibrium line, right? It can vibrate the all points on the beam is moving downward or moving upward. So it is vibrating up and down above the and below and above the equilibrium line, and this is called first mode. And it can also vibrate if this is the equilibrium line. It can vibrate as a sine wave, either above or below. Okay, so let me just take one. Either it is this half, this up to L over 2. That this part of the beam is going up and the second part of the beam is going downward. Or if the first, and of course this is cyclic, so up and down, changing. So it means the other configuration will be this part will go downward and this part of the beam will go upward. So this is a complete sine wave. And this is called second mode. And so on. So those are the elastic members will have not just a single, they are not single degree of freedom system. Okay, and we talked about this maybe in chapter 1, as in maybe here or before that, about degrees of freedom. Okay, we said that a cantilever beam will have an infinite number of degrees of freedom because the mass, if the mass is not zero, then the kinetic energy is not zero, and then at each point you can consider there is part of a mass, then and this can have infinite number of points. And this will make the system as infinite number of degrees of freedom. The Rayleigh method is to assume that part of this method is assumptions. Okay, assumption of the first mode. Okay, not the second mode. Assumption of the first mode. How is the first mode is going to be the shape of the first mode? Now I told you this is half sine. It looks like a half sine, but not necessarily equal to half sine. It might be something else. Okay, but I just wanted to give you the idea that how it will vibrate in the first mode. That the whole beam will go either, it will oscillate about the below and above. All the points on the beam will go upward or downward. For the second mode, it will half of the beam will go up and the other half will go down, or vice versa. and this is cyclic, so this is not static, this is moving with time, but it will take this shape at this mode. Okay, and the same thing for other members, like cantilever beam. Cantilever beam will have the first mode. This is the equilibrium. Okay, the first mode will be something like that, or it will go up. Either the whole beam is moving downward or upward. This is the first mode. Okay, and the second mode will be is something like that. It will have part of the beam is going downward and the second half is going upward, or vice versa. This is second mode. And there is third mode and fourth and so on. This is what happens for elastic members under vibration. The approximation that we are going to do using the Rayleigh method is to approximate the first mode. The mode will oscillate with the frequency ω1 for first mode. The second mode will oscillate with the frequency ω2 and so on. And ω1 is greater than ω2 is greater than ω1, and ω3 is greater than ω2 and so on. That will make the mode number go higher. And with higher modes, the frequencies are higher. Okay, so the approximation is we are doing approximation of one of the modes. And usually we are practicing here the first mode, because this is the most important. And this might be the most, that might be the excited mode under force vibration. So the first mode will be approximated. The shape. How is the shape of the beam under first mode is changing? And to get the exact shape, it means we have to move on to another technique. Okay, but to be within the scope of the course, we should use an approximation that this shape, which is y, as function of x. Okay, this is x is moving along the beam. Okay, and y is the deflection. The same thing for the spring. The deflection of the spring is this is 0, which means y is 0. Okay, or x. This is moving with x, and you can measure x in terms of y. Okay, what is y? Y is moving from the fixed point. So here is we use x to be along the beam. Here we use y along the spring. What is the spring velocity? What is x at y equal to 0? X at y equal to 0 is also 0, because this is fixed. So x here is 0. Okay, and x at the top is the mass, the motion of the mass. So there is variation of displacement. We have 0 at y equal to 0 and x equal to and a displacement equal to x at y equal to L. It is x, which is unknown. So the variation in the displacement of the spring between 0 and L has to be assumed. That's called shape function. So you can assume that x is equal to, since we need the kinetic energy, we will use we find the expression for the velocity. Okay, x equal to x dot equal to the spring. Okay, so this is this is x is at the top. Okay, x is the motion of the mass. For the spring, X for the spring is 0 when y equal to 0. And X of the spring equal to X of the mass at y equal to L. So there is variation in the spring deflection. Okay, so X of the spring will equal to X times y over L. You can assume linear relationship. So that satisfying the conditions, those are, we call them boundary condition. The same thing for cantilever beam has boundary conditions, right? So if those boundary conditions are satisfied by the assumed equation, then you can carry on. So when y equal to 0, then 0 multiplied by x divided by L is 0. That will satisfy the first boundary condition. And when y equal to L, then y over L is 1 multiplied by x. So it is satisfying the second boundary condition. And you can differentiate this to get the velocity. Y is not function of time here. Y is the length of the spring. Okay, so I know the time is over, so we will come back to this with the tutorial next time. So we will talk about example 9 next time. Okay. Awesome.
دكتور
Yeah.
الساعة كم الكوز؟
كوز الساعة 6:30.
اها اوكي.
On Blackboard or Teams, Doctor?
On Teams, yes.
Okay.